Hmm. Hello? Hello? Are we live yet? Am I live? Hello? Yeah. Yeah, here we go. So, pop up the chats. Will take some time until you'll hear me. Live chat. Pop out the chat. Yeah. Here we go. Mm. So, yeah, uh, I'm streaming locally. Alright. I'm also restreaming locally. I just set up a basic Nginx restream server because I tried to do the restream.io, but they the first of all it got much more expensive and not as convenient as it were, and second of all, they now force everyone to put the Ukrainian flag. They forcefully put the Ukrainian flag on every stream, and I find it just unacceptable. Because in my case, I'm doing computer science here. I'm streaming computer science and programming here, and not some politics stuff. There is so much political garbage out there. You can just I don't know, open like YouTube and see the whole stuff yourself. So why do they force me basically to push the whole political bias to all my viewers, even though I ain't got much of them. But anyway, it's really not what I wanted. So oh shit, it's I wanted to stream 1 hour earlier today. Yeah. Holy. Yeah, well. Oh, there's something. Keyframe. Keyframes, hello? YouTube reports that it doesn't work as intended. Hello? YouTube reports that it doesn't work as intended. Oh no, it works. Oh, wait, people in blocks. It's certainly not what I want. It's people in blocks. No. No, it's science and technology. It's a scientific stream. We're doing science here, computer science basically. So, yeah, I just installed OBS. I just switched to another because I normally used Windows. I know it sounds like hilarious, like using a Windows. Come on, who in the right mind does it? But as it turned out, many people do. And well, now I finally switched to Linux, to Kali Linux. Yeah, don't say anything about it. I know. Here we go. Yeah. That's sorry. That's alright. So now we have Kali Linux here. Yeah, yeah. So unfortunately, for example, OBS also um, doesn't ship the binaries as a step packages. I had to install a Flatpak, and Flatpak, it turns out it's much less convenient than I thought. I thought you just like run it and it installs, but now I figured out that I have to run the command to basically then run the app. So I had to create a shortcut, etc. Well, it wasn't a big deal for me, but yeah. And again, don't ask me why I installed like Kali Linux on my main PC. Is it about flexing? Uh, More no than yes, because I just love Kali Linux. It's just awesome. I mean, it's just very convenient to work with. It's pretty smooth. The UI is pretty awesome. There's a whole lot of stuff which works on the box. Something does not. Yeah, but uh, for a long time I had problems with Kali Linux because for some reason didn't support the graphical firmware, and didn't really support my graphics card, and I had much trouble with it. Yeah, because I have two displays, and yeah, that was something. That was pretty. That was pretty. Yeah. So it was inconvenient, but whatever. Let's start. So what we're going to do in this series is we're gonna be. I better open it. Oops. Shit. No. What? Why doesn't does it open? Yeah. Whatever. Yeah. So we're gonna open yeah, a private window for to make sure you don't see anything you're not supposed to see. No, actually, I have nothing. I have nothing to hide from public here. Yeah, even though it's kind of Linux, but yeah. So yeah, we're gonna be using OSDev, and we're gonna be writing a type 1 hypervisor, which is very complicated, and I've barely found anything, and I mean anything in the internet, and yeah, it's it can be very complicated. It's for badass dudes only who are like 100 years at the low level software kernel like development, etc. But yeah, I guess I'll just try it, and I guess like let's try it out and see whether it will work or not, and yeah, whether we succeed, and yeah. So let's go ahead. Oh yeah, and I have my oops. Yeah, and there's some small stuff already already written. Some yeah. So basically, the only explanation I found online was basically what's the difference between type 1 and type 2 hypervisor. And this is it. There's the type 1 hypervisor, this is the type 2 hypervisor, and that's basically the difference. And yeah, that's it. There's nothing more you have to know, or we know. So like seeing the profis quote, the pros, the real motherfuckers, like everyone telling the same stuff, just literally the same. It's really where I think, holy, are you a pro, or you're just pretending to be one? Because if you're trying to ask, wow, what is this, and if you're trying to go like something just a bit more into the details, they instantly start saying, oh, I'm not, I don't know the answer. So everyone is telling basically the same, and to discover something really new, really unique, you have to dig it up yourself. So there's basically there are no YouTube videos properly, and I mean really properly explaining the whole stuff. They are just known, right? There's nothing. There are no YouTube videos properly explaining the stuff and going just a bit deeper than the basic level everyone covers. But yeah, whatever. Yeah, let's create a folder. So yeah, I'll cover the stuff. I also covered the stuff pretty briefly, so you know what I'm talking about. So hypervisor types. Right, what is a VMware, they're the ones who really did the ESXi, and I'm a pretty big fan of the ESXi hypervisor. Yeah, it was acquired by Broadcom, the VMware Yeah, so the key difference is pretty, yeah, so pretty obvious. So there is this traditional, and there is this, yeah, this is the wrong one. Yeah, so type 1 hypervisor is a bare metal hypervisor, and the type 2 hypervisor has like operating system. So for example, like VirtualBox. No, it has to run some operating system system underneath. In our case, it's Linux, it's Windows, it's OS X, whatever it is. But it's, yeah. So it has some operating system, and there are also these type 1 hypervisors, which are, for example, Hyper-V in case of Windows, but it's, yeah, it's pretty type 1 hypervisor. It's basically, as a normal user, even if you're used to virtual machines, you normally don't really see the type 2 the type 1 hypervisors. Type 1 hypervisors are mostly seen in some enterprise level production servers, etc. So the interesting thing is, for example, here in Linux, if somebody's familiar, and I guess if you're watching this video and if you're watching the stream, you're somehow familiar with how it works with a KVM, kernel virtual machine. Basically, this is something in between, because it's been loaded on the kernel level, but by Linux kernel is a module, so it basically runs directly on the hardware and it takes advantage of all the hardware virtualization, but it still relies on Linux memory management, and it still relies on Linux kernel. Maybe not the GNU/Linux operating system itself, but on Linux kernel. So and it's also pretty performant. And if somebody asks what's about Proxmox, I mean, dudes, come on. If I just Google something and I see like hypervisor comparisons, and I see ESXi, Hyper-V, KVM, Proxmox performance comparisons, I'm just thinking, what the hell? What the hell did this dude smoke, or what kind of university did he graduated from, or did he even study the whole thing? But you know, even without studying, if you like take just a closer look at Proxmox, you'll find out that it's the same KVM, and it's by the same KVM. I mean, literally, it's the KVM running inside Linux with just a graphical user interface, well, the web interface in case of Proxmox, just slapped on top of it. And this is it. Proxmox doesn't virtualize a shit. It's Proxmox itself, it's just a fancy web interface. Well, yeah, they have some. I think they develop now some custom drivers, some custom Linux virtualization subsystems, but everything still relying on KVM. So comparing KVM to Proxmox is basically comparing KVM to KVM. So yeah. This is what makes me really, you know, angry, and I'm just like thinking, what the hell is going on? Okay, the stream works here. And what's about here? What's going on? Okay, the stream works here. Yeah. So everything seems to work. Let's open up Discord. Oh shit. There's nobody's contact me. Right. Whatever. So that's what we're going to be doing. And well, but somebody might ask, what is the the what is the performance difference? Why do type 1 hypervisors have like much better performance than type 2 hypervisors? Or yeah, now comes the really essential part. Not every fancy pro ultra whatever technical YouTuber with a beard and some hacker gloves, also running like Kali Linux, etc., knows about some stuff. What is actually a real hardware virtualization? And the thing is, there are, well, you can split the virtualization to two parts. Well, first of all, there is an emulation, right? So basically, creating a fully virtual CPU, you can create a fully virtual CPU, and this is, for example, how all kind of Atari, Spectrum, D&D, Game Boy, whatever processors. This is how all the emulators work. They have like a programmatical CPU, and they basically parse all the assembly instructions from the virtual ROM. You select, and they run them and display them to display, etc. But I hope you understand that this is by far, I mean, in small game applications, with the games from like 90s, 80s, 90s, it works just fine. Well, not perfectly fine, but it's more than enough. But imagine running some serious shit, for example, like some serious proprietary Red Hat Linux virtualized, etc., with some proprietary stuff and constant load. So parsing all the instructions, I mean, how could you do that? Also, like, imagine the x86-64 architecture. Imagine the size of the architecture. It's just so big. First of all, it's also proprietary, so you can't really accurately reconstruct the reverse engineer and reconstruct the whole CPU. And I mean the real modern CPU with the software. It's just, I mean, dude, it's just too complicated. It's way too complicated. So, what are we left with? There are two types of basically virtualization, and this is the real virtualization, the hardware virtualization, and the so-called power virtualization. What's the problem? I mean, if somebody studied computer science, then you probably already know. In the case of a program, the operating system like handles the program as if it were the only program currently running in the whole address space, in the whole memory space, and at the back end there's an MMU which maps the pages and addresses to real physical addresses and managing the whole stuff. But it's totally another story. Yeah. And the program, the normal user space program, I'll be talking more about Linux because it's much more easier to comprehend how it works. And it says it basically comes down to setting some registers and doing a syscall, basically doing an interrupt. I think it's the 80th interrupt, and then the interrupt, the PIC, the programmable interrupt controller, takes the control over. Then the context switching comes. The kernel is in possess of process in control of the CPU core running the whole stuff. And the kernel says, okay, I'm going to do this and that, and it then basically resumes and gives control back to the to the to the user space process itself. But yeah, but imagine running an operating system, because the operating system will obviously think it's the only thing running in the kernel in the on the PC. So it's going to do? For example, it will set up the own global descriptor table, interrupt descriptor table, their own paging, etc. And then there will come a problem. How can many operating systems coexist if every operating system thinks it's the only operating system in the kernel in the core, running on running on the CPU, running on this machine, and they want they to disturb one another, and they will actually, until you either apply a so-called power virtualization. So basically, you scan the whole stuff. You scan the guest operating system, the operating system you're virtualizing, and you, for example, this is I think what people did like 30 years ago. You replace all of the instructions. For example, set global descriptor table, set interrupt descriptor table. You just replace them with the binary patching, as it is. You know how you can patch some binary, you can reverse engineer and do some stuff. This was basically the same. You're going through all the instructions, and you were patching out the instructions which could affect the CPU to some other instructions which invoked the hypervisor call. And for example, in the operating system, was instead of telling the CPU to set the GDT, it was executing the same instruction, but it was like switched and patched to invoke the hypervisor call and to tell the hypervisor to set a new global descriptor table, for example. But it got, or for example, there are many most of the new professional big operating systems support the power virtualization out of the box. For example, if you start a Linux, you can instantly tell it, dude, you're virtualized. So it won't even try to set the global descriptor table, and instead it will instantly try to make the hypervisor call. So it's just to set all the stuff. But it doesn't. But not every operating system supports it, or kind of works with it. And there is the other stuff, but there's the other thing which is called the hardware virtualization. This is what you're talking about when, for example, you have to enable VTX in your BIOS or your EFI motherboard settings. What does it basically do? Well, there is a capability in the CPU itself, so you can basically, tell the kernel, not the kernel, sorry, the CPU core, tell it, now comes a special, dude, you're now virtualizing, now a special, a special code segment, well, the virtualized code will come, and please handle it as if it were like, here's the memory regions you're allowed to use, etc. Now go to it. It's called a VMX mode, and you have to execute the instruction VMX on, and you have to tell it, yeah, here it is, and then the kernel will really try to work with the virtualized instructions with only the special memory region you assigned to it, right? And all these set global descriptor table, etc. It will, PC just Sorry, just yeah. Sorry. So it will work with the with all these CPU operating system kernel specific instructions just normally, but it will have the possibility to every time you can tell it, okay, now you're all back from the VMX mode to the real CPU mode, and you work like, and you continue working on some other stuff, and it won't be a problem. So basically, the isolation is basically the hardware isolation. So I'm talking pretty much for right now. It was like 25 minutes, and do I even have viewers? Oh, it tells I have one viewer. Hello, but I guess it's just me. I have to check the YouTube pretty fast. Yeah, as in if I try writing type 1 hypervisor, it's like these basic same videos where professional real hackers just again and again tell me this just the same thing, that there are two types of hypervisors, and yeah, there isn't much more than that. So there's no basically way to find my stream. Only if I press like live. So what the hell? So how am I supposed to, you know, how are people supposed to search for information they need if the all just the hyped videos nobody really needs are coming out, and the real information stays somewhere behind the curtains. Yeah, that's pretty messed up. That's pretty fucking messed up. I'm sorry. So yeah. But here comes the first part, and the most essential one. As I mentioned earlier, a type 1 hypervisor. Basically, what we're going to do to write, what we're going to be writing today and tomorrow, I guess, and the day after tomorrow, I don't know. Is basically it's basically a microkernel itself. So it's a microkernel. So it's a mini operating system. In my case, there won't be any, any user mode, because we just don't have any users. The solid purpose of this microkernel will be to run the hypervisor, to run to switch kernels to modes and run hypervisors, etc. So yeah, no syscalls, no software, no real threads on it. Because, and yeah, also it will be much more secure, because there will be no bash, first of all, there will be no internet access, because I will do the whole managing and driver stuff. There is a pretty smart workaround, which I think SenV, also an open source type 1 hypervisor, took advantage of. So let's create an src and so let's create an src folder, and here inside we'll be creating which will be our bootloader file. We're gonna be creating a kernel.cpp, which will represent the kernel entry point. Well, the real entry point will be here at the bootloader, and it will jump to 64-bit long mode, enable GDTN paging, and it will switch to the kernel.cpp. Yeah. So third thing we really need, and it'll be outside of the source folder, and yeah, it's linker.ld, which be our linker file to, yeah, you guessed it right, to link the whole stuff together, and it will be for now a makefile to compile the whole stuff. Also, we'll be taking, of course, advantage of multi-boot, grab multi-boot, to make the whole thing, yeah, better. So, hypervisor, boot, up, .cfg. Yeah, grab config. And yeah, so yeah, I have to take a look at some stuff I made previously, as because it's not the first time I'm trying to do such a thing. Wait a second. And yeah. So first of all, we have to, yeah. First of all, we have to define the compiler flags. We have to define the compiler flags, and compiler collection is command will be G++. I think we're gonna be, yeah, we're going to compile the whole thing for 64 bits. So normally you have to mention like -M32, but in my case I think 64, which machine architecture and is 64 bits. So yeah. So now we have to also write NASM, which is our, well, yeah, assembly compiler. Yeah, I know the Copilot auto completes everything for me, and yeah, this is the linker. So we have to make some targets in this. So we'll be storing this in the ISO file. So compile the kernel. So yeah, this is what we're doing. Yep, this is is how it works. So we're gonna using the linker.ld file. We're gonna be building kernel.bin, using the boot.o and kernel.o. Kernel.bin. So we're creating the kernel.bin file and moving it to the boot folder. So yeah, now we have to all so yeah, that's the thing, and this is our compiler. We'll be using to compile the stuff. There is a linker file though. There is a linker file though. I think I'll just copy it from some tutorials. We could have written it ourselves, but there is no need to do it ourselves, right? So it basically tells how the data is loaded, where it's located, etc. So this is a variable kernel language where the kernel obviously ends. This will be the start of our heap stacks, etc. So the RAM stuff, BSS, 4K. So it will be round up to 4 kilobytes, which is a page size. Yeah. So it is a boot. Yeah. I think it's okay. So yeah, now we have to basically write the bootloader, and for this I'm gonna be using the OSDev. The OSDev page. The thing is, we just forgot to do something like hypervisor. CFG. We forgot to use the grub config. So yeah. So yeah, it basically tells the grub to load to jump to this file, and using the multi-boot, and this is it. Yeah, this is all we need actually. So does it actually? Yeah, I'm good. Yeah, it works. The stream works. Stream works. So yeah. Entering along more directly. This is what's the most interesting for us. So we're defining here some flags, and yeah. So we cannot. First, as the system actually boots in 16-bit, and I mean it's really 16-bit mode. It's yeah, it's that complicated because all the CPUs have to support the whole legacy shit, and it's yeah, it's really complicated. So what the system does is it boots at 16-bit mode, and it's called real mode. So you can invoke the BIOS, the BIOS, the CPU interrupts directly. You can do like direct stuff, but I think you can only access like up to 1 or 4 MB of RAM. Um, 1 MB. It's just 1 MB of RAM, which back then was like enough. I think the Apollo mission used like the Apollo mission computer had like a few kilobytes of RAM. So back then it was enough, but now it's yeah, it's a bit too complicated. But we don't have to worry about it because we're using grub, and the grub jumps to 32-bit mode, to so-called well, protected mode. Is so we cannot really, we have to clear the interrupts, etc. We can use up to 4 GB of RAM in its 32-bit mode now, but we're still pretty locked up. And I mean, just imagine the hypervisor, the type 1 hypervisor, which can only use like which can only use like 4 gigs of RAM. It's not worth it. So we have to switch to so-called long mode, and the long mode is basically the real 64-bits mode, where we can actually access the whole memory. I think it's up to some like billions of memory addresses, which is like way more than enough, and I don't think we're gonna be seeing 128-bit PCs soon, because it's just not necessary. There is no way we can use up the whole space, at least next 100 years at least. Yeah, but we have to do some stuff here, and this is, for example, the to enable the paging. So to know, because it will be very complicated to address talk to memory addresses directly. We have to, there's a so-called paging, and if you studied computer science or similar stuff, you probably know what it is. So basically, yeah, memory is split to so-called, well, pages, and every page gets some so-called flags, which describe what kind of data this page contains. So first, the page, it's just some bits, right? For the CPU to know. It comes mostly because of the security, because of the security concerns. Because let's, for example, imagine you're some dude will write some bytes to the memory, and then you'll try to execute these bytes, and this is a malicious code. And in modern operating systems, and better say in modern PCs, since the memory isn't marked as executable, since it doesn't have an executable bit, the processor will just crash, or tell the operating system, or well, invoke the interrupt, actually, right? Like fuck off, I'm not executing it, because it's not executable. This memory isn't executable. I don't know what happens if I'll try to execute it. So no, you first mark this memory page, or a whole region, as executable, and then no problem, and execute them. And so there are a few flags. First of all, that the page is the page is present, right? So that the CPU knows that this is a valid page, and it's safe to read anything from it. And second, if the page if it can be written to this page, because for example, if well, of course, yeah. Well, what we're talking about the kernel stuff here, the kernel mode here, but in context of um, the user space mode. There, for example, some like standard libraries like glibc or something similar, which is constantly loaded to a static region of memory, and everyone can basically invoke the functions. But imagine like if one application just rewrites the malloc function, or I don't know, something, and then the other application with higher permissions with higher permissions just executes this function, and it's a malicious one. Just imagine that. So this is really not that what we want. So yeah, and this is the code, and to to jump to the long mode, to the 64-bit mode, and take advantage of all the modern stuff and hardware and a lot of memory, we have to tell the CPU we're in the 64-bit mode. This is the paging, it's safe to run, let's go. So yeah, first of all, yeah, this is a basic bootloader, but I don't need it. I really need it because yeah, I have also some stuff written up here, but I'll be talking about it. And yeah, first of all, actually we have to check whether the stuff will work, but yeah, whatever. Give me a sec. Yeah, so first of all, since we are using a since we're using a multi-boot, we have to make grab know that we are actually using the multi-boot, and it's safe to boot to our kernel. So for this, there's you see this. There's the multi-boot header. This is a basic region where we describe basically what data we're going to be needing, etc. So yeah, first of all, we have to define some variables. Multi-boot. Hello. So if you're wondering what the hell is this, why is this 1/0? Don't ask me. This is these are some magic numbers we have to use to make multi-boot basically sure that this is a legit boot. This is the legit multi-boot kernel. So info, so page of line memory info. This is and these two. This isn't a real. These aren't real instructions. We're just telling the assembly NAS, in our case compiler, that we have the these are some macros, right? So can mode. No, we don't really need it. So there is some so-called magic. There's this BADB002. Again, don't ask me. There's a multi-boot specification where it's just there, and it should be there to verify that the multi-boot really exists. That there's a so-called magic number, and yeah, it's also for some verification purposes, because I mean, like, randomly getting this kind of number in the RAM, it would be a very big coincidence, and yeah, it's pretty impossible. So if we have this now, we really have this number, then in the boot process later we can really say, okay, it was really bootable with a multi-boot, and it's just fine. So we can use the information and etc. without worrying that this is that it will somehow damage the system. So yeah, we set the multi-boot flags. That you see there's a flag that the pH line that we also want a memory info, and there's a checksum to basically check again. There's one more checking to whether the multi-boot structure is really valid. So there's this and there's the structure begins. See, it's not better, but yep. I think we're according to my docs we're missing something, but yeah. Line 4. Separate bootloader. Oh, that's a good one. Oh yeah, there's actually, there's a bunch of useful information. GDT, setting up long mode. Yeah, I haven't seen this page actually. There is a blower and also a bootstrap. Well, we're going to pretty the same. It's pretty the same thing. Serials. Wait, this is just for the graphical mode. Yeah, so section of boot. We don't actually need a section of boot, do we? Oh, we do. Actually do. Yeah, it's in this. Okay, right. There's a section of boot. So line 4. So as you can see here, basically this is the start, and it's you can see here anymore, but this is the start entry point. This boot. It's basically the start entry point, and and then the start. First of all, it's 32. Halt. Be halting, and let's try whether it works or not. To open up. Oops. Yeah, I forgot something here. Kernel clean. C/boot. Bootloader it is. Oh yeah, so oh yeah. That was messed up because I instantly deleted the ISO file. So there's some chemo command. Actually wondering whether it should just be some black screen without crash or something. No boot in it. Checkpoint is in a segment. Oh, yeah, maybe. I think. Isn't that deep? Let's try to go there and just. Let's try to copy it. Yeah. So there's some more stuff we actually have to define. It's actually page present. So this is basically the page present, page right. Actually, page exec. Let's use the code segment. I have to look it up here. Just PSS. I have to look it up here. Isn't it a convention for the code segment? Isn't it a convention where you basically, because I think this the address where the code begins. I think it should be conventional. Code segment, so. P. Switch to long mode. Drop the script. IDT. Why is there an IDT? I don't need an IDT. And I drop the scripture table here. At least in my case, I don't see anything. So, whatever. Well, I can copy this the thing, but it's 64. So here, what it tells is. No long mode. I mean, I can use the stuff I used earlier, but whether it will help. I mean, it should help. It should work. See, instruction support in 64-bit mode. Yeah, it's not. 32. What kind of extra instructions are they actually? move. Yeah, so I mean, copying it doesn't make sense. This is a real pain. I know. Where's sec? It's saying here like it's actually something multi-boot is multi-boot 2 specification of this deprecated and multi-boot 2 for multiple architectures. Even DHCP, wow. It's far from complete, okay. PDF. Oh, it's LaTeX PDF standard one. Yeah. Maybe something in Quora. Let's try this one. Yeah. Exactly what I expected. It's exactly what I expected. Oh wait, I have an idea. Just take a... Just actually creating a 64-bit kernel. Yeah, it's what the... Yeah, this is exactly like the same. So, 64-bit kernel. And let's read something about it. So, doesn't contain any multi-boot headers and doesn't need any assembly bootstrap. Oh! Use only the necessary output format is specified in your label description to be correctly loaded by the bootloader. After the loader has passed control into the kernel, it should be set up 64-bit interrupt script after table and paging. Okay. Okay. Compile C flag, compile kernel width. C files with 64 freestanding. No std just see. Yeah, so script table multi-boot structure bootstrap. Setting up before and long switching on the long mode will make sure it's available in current CPU. Okay. Global enter kernel. But I actually really need this because pointer reload this selector by jumping to 64-bit mode. Jump K. Kernel main. Under the multi-boot structure. Oh, JMPK. Keep pointer. Yep. To the kernel execute. Battle loader. Oh, wow. So that's what you're doing. So basically, separately, and the kernel comes separately. Loader. Loader T. It's not what we really need, but. Let's try it again. It's better. Maybe I have to just like compile it in 32-bit and then. No, L64. It should be fine. That's what I was thinking. It should be fine. I mean, like compiling it in 64 bits. It's just what we want, isn't it? So yeah. I've got long mode to work. Where is def? Boot, what the hell? Oh, maybe we'll find about something Rust. Even though I hate Rust, but yeah. Some tests. Yes, check CPU ID. Oh, in our case again, it's no need to. Yeah, paging. Oh, I think I read the article. This image is looks very ignored from executable. Type privilege 0 for kernel, 3 for user. Ignored. Should be called segment ignored. Okay. GDT. OS def proxy poke. Huh? That looks similar to what I have. That looks very similar to what I have. Yeah, it's messy, so we have to write it ourselves. Yeah, well, I tried to grab some previous code from, you know. So this is what we're left with. So, fortunately, yeah, we could technically. This is my old multi-boot header. Let me send it to you. Yeah, this is the thing. So yeah, what we're doing here is 800 by 600 and 32. So yeah, here we're basically like telling it we're able to switch to this mode here, and yeah, why not? We can, though. We can modify the linker file and just start. Can modify the linker file for the other one. I think the servers is basically the same, but whatever. Yeah. So I use the old so it's 32. So now in section text we have to start the whole thing. So we first of all set up the stack. ESP no. Yeah. Stack top. And actually this stack top will come later. So now we're doing two calls here. It's set up the paging and set up page tables and enable the paging itself. So we're going to implement it. Set up page tables. So there is a very complex process of telling it what to do, but yeah. For now, I know I'll just copy a bunch of stuff, but yeah. Right. And obviously enable the paging. So it will loop over the all pages and send it as page. Nothing. Page. Yeah, like this. 2 megabyte. I don't think I haven't. Wait a second. I don't think. It's just, yeah. Yeah, it's just, or EX, page present and page write. I don't have to write the page size itself. Yeah. Doesn't work there. Loop EX, 2 megabyte. EX, the address of the directory. Yeah, does this look similar? Push the I, jump equal loop. Oh, it's not this. Protection simultaneously. Yeah. Looks right to me at least. But we'll see. I think since it's the huge page, I think we have to put this. Enable paging. So enable paging. Oops. Section PSS. Yeah. So it's just blinks, and it's. I think it's also it's also supposed to blink. It's the address. Oops. I'm not sure whether it works. I'm not. Hey, okay, right. It works. it works. So now I have to jump to the. Now we have to jump to the main. Can I remove this bit 32 because it's. Okay, right. Extern. Extern. main. It does something. Data segment. What the hell? No. I think it should clean out. It should really prepare the null data. I think it comes to. Looks good what it does. It's the proper way. Oops, fuck. Make. Oh no. So for some reason it crashes this stuff. Yeah. Sure, so it works, and the other way around it does not. So wait a second. I think there was a question back then. What was the forums? Forum login. So like search. There was the one question that I asked because of the when the bootloader jumps to a kernel's entry point, the EBX contains the pointer to the multi-boot information structure. So the EBX. No, there isn't it. We're using the instruction loads available from memory using the pointer. Yes, IABX. Yeah, that's it. Load. Multi-boot. To ESI, first argument. I think it's APX, is it? Load from entry point. Oh, okay. Now we jump, but in this case we jump to kmain, the kernel main. In this case, we jump to the kernel main. Yeah. We jump to the kernel main. Am I correct? Oh. Yeah. No, it is extern. C. Main and loop forever. Let's try doing something here. Character. Let's point to the video memory. Oh, it was a world. So yeah. Oh, undefined reference to key main. Oops. And yeah, it crashes. Of course, yeah. Why shouldn't it? Why shouldn't it? Why should it crash? External key main. But I linked it. Did I? I certainly linked it. Kernel.o. Yeah. Otherwise it would like result in error, would it? Oh, I think there is one. It's a bit 64. Oh yeah, it's 64. Maybe this is why. Nope. I mean, I did it somewhere around. I found a way around. Bootloader. What I did, according to tutorial, of course. Loader the ASM. That's what I did, and so this, but this is wrong. EX kernel key. So yeah, that was wrong. External long mode start. Double long mode start. Okay. Sorry, I have to check something on my end. By the message. External long mode start. This is the long mode start, and this is the key main. And the bootloader itself. What does it do? It loads the global scripture table and jumps to the And this is what I did wrong. And the kernel not ASM. I have to add it to the file. Symbol key main. It's not. What the shit? External C void key main. Oh. Yeah. I'm just stupid. Yeah. And here we go. We have hello. Yeah. We have a hello world. Yeah, it's in 64 bits. It's a 64-bit hello world. Yeah. Because, well, I don't know. I'm not sure actually how to. It's separated for sure. Print. Fuck. Print. again, I'm just trying to learn something, so don't expect me to really know the practical stuff. I know I somehow know the theoretical stuff, but not the practical. Yeah. Yeah, it's using the CPU ID. I guess it's right. Estimate. Hmm? Huh? No, there's an operand. What the shit? That's something new. Maybe I guess it's because of the mode, but yeah. Stand. Nope. Yeah. So volatile. Yeah. So it's Oh. Okay. Okay. Huh. 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 That's strange. That's really strange. First of all, the system's running just fine, but if I messed up, it's. Wait, I have some code to verify it. I've already written some code to verify it, which works. Which just works. I guarantee. I think that was in the main. Yeah, there's a bunch of code to, Yeah. There was a bunch of code. Yeah. So yeah, we have to define types. Yeah, it's enabled. Yeah, but that was, CS. CS should be pointing the 64-bit segment typically. CS. Yeah, so I know it. But the old code showed that the mode was wrong, but definitely should work. It definitely has to work. Like it just has to. Create This is the header on the library. And forgive me, I have to make a small call. Because yeah, I just had to. So let's continue. I'm sorry. So I have this multi-boot structure here. I just found, oh, it's actually OSDev. It's some OSDev tutorial. So some dude making an operating system and making pretty the same thing as I did, but oh yeah, it's actually worth taking a look of. But try to take a look at it. Oh yeah, yeah. So, but it's just a 32-bit system, so nothing. Nothing. Address or say wait, let's remove the whole stuff for now, but except for print, because we're gonna be needing the print, but the whole stuff not now. Let's do some. Yeah, like that. So, put a print on the world first. Yeah, it works. Fine. Then there is a pointer to the multi-boot header. Oh yeah, I have it, of course. And oh yeah, multi-boot header. Multi-boot detected, right? Wait, it's not the power magic number. This is the actually the proper way. And I think it will work. Yeah, it won't. Because I guess we didn't really pass the kernel asm, and this is the kernel main with the kernel. Convention version guide. Yeah, and this is the last time I traveled with the multi-boot, and I don't think the structure has to contain this magic. I think the magic is always separately, comes always separately. Magic number, because it is. I don't think it passes anything to When the bootloader invokes 32-bit operating system, the machine must have the following state: EAX. EAX. So EAX has to contain. Yeah, the EAX has to contain. Presence of this value indicates that the operating system was loaded with multi-boot to compliant bootloader. But this is the thing, isn't it? Well, I'll see how it's boot S. So valid. Job equal error. Let's just hold for now. Let's just hold it for now. Yeah, it's wrong. The ESI. Wait, where is? Prop. Yeah, base low, base high. Yeah, I see the same PDF as earlier. So modules, the structures. Yeah, blah blah blah. Information. Must boot. Probe with information. Ha ha ha. Okay. Interesting. Actuators. No, it's the interrupts. Multi-boot. Well, I've seen a way to, check whether the multi-boot works. Well, I check multi-boot. Wait, according to this docs, the EAX should be the multi-boot number. EAX multi-boot magic to EPI. Nope. Hold. Oh, it didn't even. No, it didn't even reach the one. Oh, yeah. Compare the EDI. Just the magic number. Valid magic number. bed B002. And the bootloader is B002. So it's not properly passed, and this is what I was expecting. So EAX. I think we have to store the EAX somewhere. So, hold. Oops, yeah, I didn't do anything here. So, what? So the subroutine starts subroutine, right? Okay. Oh, wait, so it tells me that the multi-boot seems not to exist in the stuff? What the shit? It's impossible. It says, yeah, it's definitely booted using multi-boot. Just have to compare the EAX. Isn't it stuff? And just compare to EAX and jump not equal if it's not equal. Wow, so it doesn't seem to work at all. And why doesn't it seem to work at all? Yeah, because I messed up in the file, the linker file. Oh no, it works. It should work. So it was booted without the... Let's try it again, but page size. Oh, yeah, I was right. It didn't work because it's called multi-boot header, and this is section multi-boot header. Huh? This why didn't work? Oh, it still doesn't work. Shit. Multi-boot header. This is basically the same stuff. Page present is on the oh yeah, just forgot the proper pages. Yeah, that makes me wonder, what am I actually doing here? Jump not equal. Zero. Bed B002. So apparently it's not stored in the. Apparently it's not stored in the EAX register. Or I don't know. I really don't know. Yeah, multi-boot 1 magic number. PAT version 0. Battery start. So there's just no way it shouldn't work. Keep multi-boot error. Section multi-boot header. Maybe I have to separate it to the separate file. Fasten. Make file. There we go. Magic is not defined. Oh, yeah. Yeah, of course. And the magic is here. Yeah. What the hell's going on here? But maybe there is. Maybe some additional checks. Well, in this case, it works. Magic number. See, like. Passing parameter and the registers. EX. Because the EX that's the EX. Sorry, EX. Yeah, but it's being used multiple times, so there is. Where do I have section data? Error data. Oh, it says it's at the bottom. Magic x00 and here number from EAX to input magic load to EBX. think it should be EPX, shouldn't it? Now we want to see it work, but on the kernel, I'm not sure actually how to share the. Can I make it go like this? So that's this is the section files. First message, second message. So how would you technically? I mean, will it work? Doesn't look that way. Oh, wait, that's. It works here. It works. It really worked. Huh? So I have this magic, and it's valid magic number, and I guess check the for validity. The world. So B. Yeah, it seems to work. Hey, somebody just joined the stream and just instantly left. What a shame. Maybe I should turn on the music. Maybe. Again, at least I'm learning something out of it. Something CS or stream. Is there something? Oh, this is an advertisement.
Autowert.
Yeah, it should work. It's much better though this way. Yeah, so multiple H, and this says unsigned no magic. no member named Magic? Huh? Struck multiple info? Oh. Oh. Oops. Oops. Map. Memory map. So. Memory map T. I think that's a good idea, but memory map. Oops. Yeah, I just messed up the namings because it was like renamed here. Hope it doesn't crash. Did it just? I'm afraid it just did. I'm afraid it just did, but wait. Huh? Wait a second. How's it possible? If it should, then it should crash after this stuff. Memory map. So memory map. Yeah. Okay, that works, but CPP. Oops. Yeah. I'm just stupid. Messed up a bit. Okay. Physical page start. So I have seen a very good tutorial on it. Memory layout, there's some very good some. Yeah, so I just found it and let's rock and roll. Stupid advertisement. I mean, I have YouTube Premium on my other account, but oh yeah, there it is. Nope. So will it work? Oh. This. Oh. Map entry was declared as scope size of map entry. So it seems to kind of worked. Fortunately, I have some pre-made files and drivers. VGA.hp. I'm migrating the drivers and VGA.cpp. Oops. Like this. So it basically enables us to print the digits, right? So yeah, this is something I've did a couple times ago earlier. So yeah. VGA.cpp, the VGA file, and here we're going to be adding include driver/VGA. It's a printf. So now it's going to be working. Yeah, there's a bunch of memory here. Oh, this will work? Nope, it does not, because yeah, this is basically the same reason why this is basically the same thing I mentioned at the at my post. I guess there's an interrupt happening, and this is why it instantly reboots. Yeah. So I guess this thing just invokes interrupt for some reason. Yeah. Actually, I'm not even know. It's aren't that much. Wait, let me just. Yep, let me write a small post about it. So, there was a pretty nice OSDev topic. OSDev. Detecting memory. Detecting memory of about 4 gigabytes. Yep. Main is the thing. But I'm wondering why is it? Dude, it should be the I don't know. Wait. Printf. Wait for now. Magic. BT002. Yeah, it's correct. It's definitely correct. So, multiple info T. This whether check if yeah. So it definitely seems to work. It should work. There's no way it doesn't. So, for some reason it's swapped out here in the info. Oops. Let's just rename it. Oops, panic. Yeah, it should be printf. So it's there. It's definitely there. So it's basically protection to, you know, what? T. Oh yeah. Yeah, I don't use the normal map T. Size of memory map T. Multi-boot memory available. Huh? Oh, well, we'll just leave it out for now. T. It's maybe, it's not len, it's maybe size or wait, maybe it's much better to take the original multi-boot instead of the fake one. Find multi-boot error. Just copy the stuff from the. Just copy the stuff from the. Panic, yeah. It's a panic. It's just printf. Yeah, hey, it works. It was really something, you know, messed up with it, and it should look that way. Actually, it should. So I think we could finish for now, but I actually do not want to. But I think for now we should push it to the Is there a way to calculate it, how much memory it was, you know, alright. Let's send some more memory. memory. Yep. Huh. Yeah, it's pretty messed up. It's pretty messed up. Let's just use a normal integer. Is there a way to properly calculate in memory? I mean, is there? Minus, I mean, it's some pretty much stuff here, but length. The only way I'll know it works, it's when I get the full RAM available. You should use in place of mem lower and mem upper as indicated in the OSDF wiki. Oh yeah, this is basically the same thing. UFI, memory map, this is some legacy stuff. Let's try and ask the ChatGPT, for example. But yeah, I think I should push it to the GitHub, but whatever. So let's ask. I have this simple memory map. Yep. Hello? ChatGPT? Hello? What am I paying you for? Mr. GPT? Mr. GPT, hello? I'm paying for premium. Well, it's for the university, of course, but it doesn't seem to work now. It's just fucked up. Let's try to feed it like in there, in the Copilot. Yeah, but LAU. What does actually LLU mean? Well, obviously not Loma Linda University. Pretty enough, yeah. Let's modify it. I think it's the same as you. Whoa! It actually works! Wait. Yeah, it actually works! Let's add 12 fucking gigabytes. Haha, it actually works, and I think it's either the rounding error, or it's the either the rounding error or the memory or the kernel just using up this 1 megabyte and telling it, hey, no, I have my code here, don't touch it, and it's more than enough, and it's just rounds down to this, or it's just some kind of, yeah, I think it's because of the rounding error. But look, it detects all the memory. It indeed detects the memory, and it's more than you know, the 4 gigabyte. Just let's do small benchmark. Right, gigabyte of random data memory. Read. Yeah, it crashes. I don't know why. Maybe I'm not doing the right way. Yeah, I get it. I'm not doing it, or not doing it the right way. But look, it detects it definitely detects the more memory. I mean, obviously, yeah, obviously I can directly write it because I have to do the page swapping and several other stuff, but it definitely isn't the worst thing. It definitely isn't that bad, and it works. It doesn't only look like it works. It actually works. So it detects all the layout, and it seems to properly detect all the memory available. So without a doubt, we succeeded by doing this. Right. I'll make a small pause, and I'll pretty soon get back to you, I guess. Yeah. Where the Twitch, YouTube. Well, my old code. With all the interrupts. Because we'll be doing interrupts now. Before I really push it to the GitHub. Or the text. Obviously, yeah. Obviously, I can memory the 4 gigabyte. Just let's do small benchmark.
you think we're done? I recall the past again tonight. It's in the front of my mind. As I fall apart, you begin to cry. The tears are making you blind. The future's far away, but I will stay. I will stay. Just take a leap of faith. We'll find a way for you and me. Can't look back and run from what I feel inside. There's no more time to hide. Because I feel again. I feel again. Oh, now I feel again. We're bringing this back to life. I feel it again. I feel it again. I feel again. We're bringing this back to life.
Hey, so I'm back. I'm back, and yeah, let's continue. Yeah, let's continue and create some interrupts. Yeah, so for example, we try to, you know, let's invoke the crash. Let's use an expression so the compiler doesn't, you know, remove that. They just write 1 divided by 0. The compiler will auto remove it because it's nowhere near. But pretty enough. Yeah, let's just try to run it. Yep, you see, it's oh, I have to remove the text. Yeah, you see, it's just invokes the basically the interrupt the error, and what the CPU does is it restarts it. To do it, we have to set up the interrupts. First of all, we have to program the so-called PIC programmable interrupt controller, which basically, instead of like just crashing the whole PC, imagine you're just open the Python and divide by 0. I mean, the Python is obviously too smart for it, but imagine every time you're dividing by 0 or any error happens, either, well, in our case it will be the blue screen of death, kinda. But imagine the everything just crashes. It's obviously not what we want, right? So yeah, we have to deal with the interrupts for now. First of all, we have to create. Well, we're going to be using. We're going to be needing some utilities, some commands. Oh wait, it's way too loud for me. Yeah, it's way too loud. It was way too loud for me. Yeah. So let's continue. So yeah, some utilities. Let's create a new file and create utils.hpp and just in the root directory, because they're going to be used pretty often. So, and utils.cpp, obviously, if not defined, utils hpp defined, and if, so it's not included multiple times, and we have no redefinition errors. Well, we can connect this to the int. Let's define it in the VGA driver, the memory. What we're going to be doing is, first of all, void memset. Then void copy. Start. Yeah, that will be actually it for now. We won't be needing much more. Sorry, I just have water. So yeah, then the stuff's gonna start. We'll be starting with the interrupts. And we'll be taking advantage of the so-called. Yeah, I know everyone does that, right? And it's pretty lame that everybody's doing that. I mean, taking advantage and using the assembler, assembler preprocessor and in macroses, but it's really first of all, it's really the easiest way, and second of all, this is the proper way to do it. It's really the one and only proper way to do such thing. To do such thing as interrupts. But you'll see it's not as complicated. For me personally, I think 1.5 years until I really figured it out how the whole thing really works. Not not just like copy pasting stuff. But again, more of a like how real interrupt works. Yeah. And it started to make sense. Many things started to make sense. First, let's create idt.hpp, which is header file. We didn't create the cpp. Oops. Yeah, here we go. And we have to obviously edit. /cpp. Yep. Yep, it works. Yeah, and it crashes because we have the division by 0. So yeah, let's go to the intro description.hpp. cpp, obviously. So we have to define some stuff. And yeah, again, it will be. I think I'm not the one who can explain the stuff really good. So yeah, I think I'll leave some links in the description to some videos where it's first of all, it's implemented pretty similar to what I've done, and part of the implementation I take some code from them, but just adapting them. I think I'll leave not the whole code, but partially the code, or better to say again, concepts. But I think I'll leave some links in the description to for you to figure it out and be taught by how it works better than I. So somebody can really explain how it works, but because for me the main goal is to today at least get to the basic VMX calls or VMX virtual instructions. So I have to do it like really fast using my the stuff I already sometimes I've already written some time ago. So yeah. Yep. This is the. So we have some install handler. This is again, this code is pretty similar to what you could see later, but not exactly the same. First of all, because most of the people do it using C, and I'm doing this with C++. You see the external C. I wasn't for a long time. I didn't know why it doesn't work and why. For example, assembly tells me that the ISR and the RQ handlers are basically don't basically work and are undefined, but they definitely are defined. But yeah, but then I found out shit. It's C++ and I'm using G++, so the naming convention in C++ is different. How it's being compiled, you can, well, not guess it, you can see it and you can use it. There was the one guy, the German engineer, I think his nickname was Algorithmen, I think Markus Engelmann was his name, and he was writing the pretty same thing on his channel, writing your own operating system, which is also very good. It's a bit outdated, but back then when I first tried to do something similar, this was the only channel, and it was pretty new back then, and I didn't understand much. Now when I started my my university career, it's obvious what he does, and it's simpler to comprehend. But back then, yeah, it's a bit outdated, but it's still pretty good, and it's pretty good explained. So take a look at writing your own operating system from Algorithmen, and he does it. Why am I talking about him? Yeah, because he does it with C++, and he does this interrupts. The interrupt handler with C++, and he was talking a bit about C++ naming convention and how you have to call these functions for them to be linked with the assembly, etc. But we'll keep it with the extern C, so it's easier. I know you can like put extern C up here and use it as the whole it's all extern C block, but I think for me it's better to this, because you're sure for every single function. That's yeah, I think it's much more convenient, but you can do as you like, no problem. Oh yeah, I forgot something. What I forgot is the interrupt registers. Because when the interrupt is triggered, you have to be sure what interrupt registers where are and what states they have to be, sure what this interrupt means, what it triggers, by whom it was triggered, etc. So it's pretty important. Yeah, it's pretty important. Yeah. This is it for the interpretable HPP. Yep. IDT dot. I think we can go with the so we have to define the interrupt structures and IDT flash. Yeah, the function IDT flash will be coded separately. So yeah, I'm just gonna be copying out the, the whole code. Yeah. Oops. The whole code. Briefly to say what this thing does is it sends some commands using the output port B is this is some verse. Well, you're basically sending these signals to the PIC, programmable interrupt controller, and yeah, this is it. You're sending the signals and you're basically preparing it to the. Then you're setting these gates by setting these entries, and then you flash it to you basically save to the controller's memory. This is this is basically low level. It's extremely low level. Yeah. Here we can, and this is basically how for example how it's ISR handlers, how it's handled. Yeah, I won't go much into details because yeah, except nobody's watching, so I should have ID.s. So yeah, this is obviously this isn't my code. I did some micro adjustments, but it isn't my code. As you see, it's just formatted. I think I have to mention it. This is my code taken from. I think this was the one microkernel I disassembled, and they used exactly the same code like in the yeah. So taken from wait, let's mention the YouTuber who is really good at explaining this stuff. Oh yeah, it's Olive Stem. Yeah, let's just mention him here because it's to be fair, I'm pretty fair. It is in my code. First of all, I'm not using caps lock. Even though I'm the one guy who even on the SQL doesn't use the caps lock. Yeah, and let's save it. Let's modify the make file. Yeah, oops. Slash interrupts IDT IDTO lesson. IDT.cpp IDTO instructions not supported in 64-bit mode. Shit. Oh, wait. Bis 32. Will it? Oh. IDT.cpp. Oh yeah. It's a HTTP file first of all. Second of all, driver/ega.hpp, obviously the IDT.hpp, and it won't be able to find the output B. Correct. Correct. So we're gonna be creating another, actually pretty important file. Note HPP and asm.cpp. Def. Wait. Yeah, output B. Actually, we could, you know, import B, but will be this file will be important later. It will be important. So. Import B, yeah. Drop service routine. No, it's editing in one file as cpp. Import B, huh? Oh yeah, of course I didn't include HPP. What's the problem? Printf? Oh, yeah. Printf. Huh? Huh? What the shit? Oh. Yeah, I'm stupid again. Yeah, of course. And it crashes, why? Fuck, of course, we have to. Of course, we have to. Come on, please. Holy shit. Doesn't work. Why? Huh? So now the IDT itself crashes, huh? Well, that's interesting. Because I used exactly like this same code like always. And I guess I know what happens. Yep. So flashing the IDT. Flash for some reason. Restoring the, and I know what happens. I mean, restoring the interrupts. And the interrupts are always very complicated for me, but yeah. We're restoring the interrupts. Yeah, cause I think the interrupt should be in the 64-bit mode. Unit. Cause I think the interrupt should be in the 64-bit mode. But I don't know why I tried to use this 32-bit interrupt and it kind of worked. IDT initialized. So there's something I did and it worked. And there's definitely something I did. It worked. IDT load. Oh, I did it. Yeah, that's not the code I. Oh yeah, this is not the code I actually used. So wait. 47. IDT load. IDT load doesn't declare in the scope. IDT.cpp. IDT load. Oops. 5. Oh, jetzt ist es passiert. Shit, I have to do something with it. Verbal field declared void. Yeah, that's the code I've written, which is a bit different. Mm-hmm. Yeah. Trained? Yeah. IDT load. Western C. Yeah, that should work, actually. Actually, it should work. What do you want? Fuck. I'm just like disable the, yeah, disable the warnings, because who cares? A variable of field ID to load clear the void. And it crashes because it doesn't because it doesn't load the IDT, and it still crashes for some reason. I don't know why. Ah. Wait, let me. Let me do something. Yeah, I ran into some issues here, but please some stuff here. OSM. He wasn't. He said gate. Isn't clear in this scope. Yeah. So now it didn't crash. Yeah. So did my code work? It's on the way to find out. Yep. See, received interrupt, 0, division by 0. Yeah, so, yeah, seems to work. Magic. IDT initialized. So yeah, we have again. Here we are, boot magic. We see the boot magic. We see the IDT, right? Yeah, we have like start addresses. We have the total memory here available, and yeah. So we have basic interrupts. We have basic memory, and we have actually it's a 64-bit memory, so we can access more than that. We can really access a whole lot of memory. So yeah. But first things first. H. Oh no, it's not the one. First of all, mem set and out B. CPU supports. Well, it would be a nice name, but as not HPP, which is basically just the same. Oops, no, it's not. Close the whole thing. AD, no, AS and out B. B. Import B. Also IDs is CPP. yeah, we see. I think it works. Everything works. Yep. Here we are. Um, so I'll make a small pause and we'll continue. Continue to. In our case, it will be basic, at least, VMX operations and how to, yeah, manage the stuff. Oops, yeah, I just accidentally disabled the music. So yeah, I have to do some GitHub magic. I wanted to have as a repo. In fact, I'll create a new repo just now. What time is it actually? Oh, it's it's pretty late. It's pretty late. Let's see at the YouTube. How long am I actually streaming now? No, not upload the video. I want to see my live dashboard. For how long am I streaming now? What? It's just like, oh, it's an average duration. It's been 3.5 hours. Okay, 3.5 hours. Let's break it up. Repository. Desktop. Select. Open a new window. One sec. So, yep. Provider back. Copy folders. Yep. One of the green. Should be green to you know. What I don't want to do is, first of all, no O files, no ISO files, and no image files. There's still, yeah, there's still enough. So shell commit booting to 64-bit. No. And the code has been pushed. It's, oh yeah, it has to be indexed now, but and it works just fine. Yep. Was it indexed now? No, it wasn't. Right. Not a big deal. So I'll be back pretty soon, and yeah, see you in a couple of minutes. So I'm back. Yeah. Um, so now when I got everything set up, um, drivers and interrupts, the really hard stuff begins, because we have to well, we have to deal with a basic VMix. At least I'm not actually hoping to having achieved the the proper VMix operations by today, because first things first, we have to implement the memory manager at first, but with the proper paging, switching pages, marking pages readable, unreadable, etc., etc., etc. This is not what we're going to do today, because first of all, I'm a bit unprepared, but okay, I wasn't prepared for the whole stream, but whatever. Yeah, because it's too complicated. It's well, it's 12 a.m. You know, I had the whole AM PM stuff. It's 0 o'clock. It's 0:22. So yeah. Maybe I have half an hour more, and then I'll have to do something, because I have fair to say, I have a small piece of homework left. Especially, I'm not sure whether it's still tomorrow or not, but I'll do it pretty quickly. It's not a big deal. It's on the Java. It's for software development course at the university. So again, not a big deal. But yep. Yeah. So I won't be able to write a fully functioning, even copy paste fully functioning memory manager today. Yeah. So what I want to see is whether write some essential CPU functions, and see whether the CPU is able to try and actually execute and get the CPU flags, whether it's able to run virtualized stuff, etc. But first, let me yeah, whatever. Let's. I've seen a pretty damn good article about it, about virtualization, where some dude, and this is the nearest nearest possible thing I've seen to the topic I want. The nearest possible thing I've seen to the topic I want. It's the hypervisor. Basically, writing a non-hypervisor inside a Linux kernel, but as a as a kernel module. This is, yeah, exactly, developing my hypervisor from scratch. Yeah, so I'll make it a bit smaller, then I'll resume the music. Oh no, I don't want YouTube music, because I get copyright striked. Let's see us for stream. God damn it. Fucking advertisement. I just fucking hate it. Especially because I pay on the on the other account, but I'm paying for a YouTube Premium. Yeah. So, I've already seen some dude developing, yeah, here we go. Developing a hypervisor on, also a kernel, like, it's more of a like, yeah, driver, kernel module hypervisor, but it's on Windows. Yeah, motivation. So developing kernel module. Yeah, you see that's, but since Linux is much easier first to develop on, and much easier to compare the your bare metal code with. Yeah, you know what I thought like yesterday or today in the morning. When I finish my studying, and I will master the whole stuff, so I don't have to struggle with the whole graph, like bootloader stuff, etc. Mappings, interrupts, etc. So when I finish my study, I will maybe go and I will maybe do some research. I will maybe stay at the university and do the research on hypervisors. That could be pretty interesting. Vmix support. Net Vmix operation. So yeah, this is the CPU idea. So the folder hypervisor. Utils.cpp. Modify it. I don't know whether it will work or not, and in normal case it does. Why isn't it highlighted? Oh, that's a lot. Yeah, it still works. It just looks more beautiful. So, how to comment actually? cd slash hypervisor slash no slash utils. Yeah, we'll be storing all the hypervisor files separately. Yep. So here we see utils. Def. HP. Hypervisor utilities. So So, yeah. Why does it actually pass the void here? I mean, there is some. I think it's a kernel development convention or something. Passing the void to the parameter, so they yeah, I don't know. Oh fuck, that's the wrong. Actually, yeah, I wanted to implement a function the CPU ID, but since it's without a CPU ID, yeah, I'll just copy paste it. Who cares? So, 'Linux not supported. Linux not supported. Huh? Huh? What does it mean? Make. Oh, nice. Oh. Why does it? What the shit? IDT initialized, total memory. Unix support. Huh? Where was it written to? Huh? What the fuck? I didn't realize. So. Maybe it's because of the git ignore, I don't know. There's no way it doesn't show up. There's also no error whatsoever. Is there? Provider look back. It's backed up for some reason. Terminal. Oh, for some reason it was in the old directory. VMix not supported, right? Okay, yeah. At least we got, yeah. At least we, yeah. So. Uh. Uh. Yeah, I have to enable it, I guess. Or at least officially check whether it works, and it certainly does. So. Your mix not support. Huh? Yeah, that's lame. Uh, so yeah. Your mix no support. Yeah. Yeah, I know it's the fifth bit here. Mm-hmm. Yeah, mix no support. Resume support. But still, it's still somehow reports that this VM is not support. VMX no support. Yeah, what? How do I have to deal with it? Check the support channel, CPU. Uh-huh. Do the emulate CPU KM64. Okay. Makes no support. SEM. Oh, at least I mean there's an error, but how does it work? KM64. Oh yeah, maybe it's because of the cost. VMX and support. Holy shit! God damn it! Why? I really don't get it. And the next time I go to the university is like the next week. Shit. So basically I'm... Shit. I mean, I could have tried booting from it on the real hardware. I mean, I'm not even sure whether I have one or not, but whether I have one or not. Nest virtualization. KVM Intel. KVM AMD. Libvirt. Shit, I had the Libvirt. I tried to do something with it, but yeah. Wait, is it VM support? Write it for AMD. Maybe it's application specific. Maybe it's because of the host. Can mix and support. VM support. Oh, I don't have KVM installed. Holy shit. Holy shit, maybe that's why. Mix and support it, okay. That should be one. So yeah, this will work. Yeah, mix and support. Shit. Yeah, mix and support. Yeah, there's there aren't many things that I can really do here, except for going to the university and asking there. But I think for now, I'll leave it as it is. Yeah. So thank you very much for watching. If anybody is watching it later. So wait. Yeah, the only file is a multi-boot file here. It tells me there's a lot of C code here, but the only C file here is recognized as such is the multi-boot file. But yeah, there aren't many files here. But at least it works. It's in the 64-bit mode, the kernel. The memory is mapped, so it's ready for memory management. For real memory management. Yeah, so I hope you like this video, because again, nobody watched me. That's pretty sad, because it's a very interesting topic. But yeah, I hope you like this video. I hope you like the stream, and I hope future me in the future I'll do something out of it. I will do hopefully something interesting with it. So yeah, thanks.